Computers, the complexity, the ingenuity, the magnificence, the different parts that make them up. That's what we'll talk about today, starting rather simply with the PSU, or the power supply unit. This is the part that's responsible for powering the whole machine, but most people underestimate just how much power it provides. Let's take a diode, for example. This diode right here happens to consume 0.04 watts. Then we'd have a light bulb at 9 watts, a ceiling fan at 60 and a light bulb at 75, the humidifier at 240, and how large is the output of a PSU? Well, conveniently, my PSU broke 2 days ago and I had to replace a cable, and I've been running my PC on a backup ever since, and so we can use this as an example. Here's the backup and here's the current one. The backup has wattage equal to 600 watts and the current one with wattage equal to 1200 watts. Yeah, modern day PCs may seem really slick, but they still consume crazy lot of energy. And PSUs may seem like just glorified cables, but you have to remember that with our 1200 watts, we could easily fry every single other part of our PC. And that's what PSUs are for. They are for distributing a lot of energy over a lot of parts. Too little and they won't work. Too much, they will fry. But what is this they I'm referring to? Well, that'd obviously be the motherboard, which connects all of the different parts together. And it might seem like a simple part, but you have to remember that we're not just connecting two different cables together just so that current may flow. No, in reality we're connecting together logic pieces, with some of them having 1300 pins. So it's not really like connecting two cables together, only connecting thousands of pins together and determining which logic should go where depending on the other pins. It's less like a cable and more like a switchboard, except way more complex. Way more complex. It works hard, and that's why it gets the biggest PSU cable, to power all of those parts like storage, and as the name would suggest, it stores information. You can imagine storage like batteries, so with a battery you can charge it up and discharge it down. So for example, if you had a system in which you'd have an intern stuck in a box, you give the intern some random image and you want the intern too. If the image contains a dog, the intern has to charge the battery. If the image does not contain a dog, the intern leaves the battery empty. Now, after you pass all of these images through the intern box, you can take out the batteries, and now you've got an electric system with all of the dogs labeled. So basically for each image you have a bit of information representing if there is a dog in there. That's how you can store information, but usually we need to represent something more complex than just singular bits of information. So how could we represent these more complex things? Well, let's start with how could we represent numbers, like 86, for no particular reason. Well, what we could do is we could take the two batteries, charge the first one to 80% and the second one to 60%. Now we can just read these percentages, and that's the way to save numbers. Great. Except, what if you're trying to make a smaller kind of a PC? What if you're trying to make a smaller kind of a PC? Well, then you'll run into a certain issue. You see, when batteries get really small, then it becomes rather difficult to read these percentages and charge these percentages. Basically, it's really easy to charge 10% of a watt, it's just 0.1 watts. But when you're dealing with milliwatts or microwatts, these will be way more difficult. I mean, just imagine trying to measure half of 1 kilogram of water. Simple, it's half a kilogram, just drain some water out, 0.5. But what if you're trying to measure half of 1 milligram of water? Well, you're gonna drain half a milligram? I mean, you could, but it would require much more specialized equipment. And also add the whole measuring all of these millions of times a second in an unbelievably complex system, and what are we to do? Well, we can simplify the problem. Instead of asking, how much water is there? We can just ask, water is there? And that's precisely what we do, and also why I flashed the bit on the screen when referring to it, because it's not just a little bit of information, but also because bit is the simplest unit of information, which can either be a 1 or a 0. But hold on, that still won't solve the initial problem. How are we supposed to use these bits to represent numbers? Well, if you think about it, the whole numbers representation of percentages is a bit arbitrary, isn't it? I mean, why is 100% full? Why shouldn't be 120%? Why not 80%? Or why not 1? Well, it's because we just decided that, mostly because of our decimal system, deci, meaning 10, because we have 10 digits. You use up to 10 digits and then you move on. Which probably was set this way because we have 10 fingers, one per each digit, except then we also need a digit for 0. Whoopsie. The point is, you can represent numbers using 9 digits, or 8 digits, or 7 digits, or 6, or 5, or 4, or 3, or 11 if you want. Just use letters then. Oh yeah, no, 2 I guess. I suppose that would be more relevant given the fact that we can treat our bits as just digits of either 1 or 0. So just how we can represent a number with 1s and 0s in a binary system, we can also do so using electricity. So that's how you can think of storage. Obviously this whole video should have a massive asterisk plastered on top of it, but that's the basic gist of it. Except there are different kinds of storage, like storage, RAM, or random access memory, or just memory, and cache. So what's the difference between them? Well, the difference is simple. You see, making quicker kinds of storage is more expensive, but you need both quick and large storage to function, and as a consequence you have massive but slow storage, you have moderately fast and moderately small memory, and then really quick but tiny cache. Cache is so quick in fact that you couldn't really afford to move it further from where it's needed, so it's still in there in the CPU, so the central processing unit. Let's go over the name from the end to the start, with unit means just like a single thing, so that's it. That's a unit, so I guess I haven't really explained that, have I? Processing means data processing, and this one will take a bit more to explain. So let's use my favorite example, adding. How to add two binary numbers together. In order to understand that, we'll have to go over logic gates, and there are only 3 important ones. There is the NOT gate, the OR gate, and the AND gate. And here's how they work. NOT lights up when the input is not lit up. OR lights up when the first or second input is up. AND lights up when the first and second input is up. That's kinda it actually. Computers are hard, aren't they? So now that we get how logic gates work, let's go over to the more complex example with addition. How would we add two binary numbers together? Well, here I've created a table of all results, and from that table we know that this should light up when the first and the second are both up. This should light up when the first or the second one are up, but not when first and the second one are both up. I will give you a second to digest this sentence. Then the circuit based on the sentence, and then this animation yet again to really understand. This is how it works. Now let's move on to something a bit more complex. 1 bit more complex to be exact, because we'll add together 3 different numbers. Well, here's the table for adding 3 numbers, and I'll leave this one on the screen for a bit longer because it is larger, but you can clearly see the pattern, so it should be simple. Now, when should this one be up? Well, we already know this should be up if the first and second, or second and third, or third and first are both up. So now, just like before, we can just turn this sentence into logic gates, and that's it for the second bit. Now the first bit, when should it be on? Well, it should be on if the result is equal to 1 or 3, but unfortunately we don't really have a gate which is called is equal to 3 or is equal to 1 yet, so we'll have to tackle this manually. So what we can do is we can say that if the first or the second one or the third one are active, then it should also activate. Which means that if either one of them is active, or if all 3 of them are active, it activates. But there's one small issue with this approach. You see, if only 2 of them are active, then we get the result of 3, when we should get 2. So what we want is we want this to light up when at least one of them is active and not when two of them are active. So now we just need to add the last line, which means the first and second and third. And there we go, now we have an adder, which adds 3 numbers into a single 2-digit long number. And it may seem like just any other tiny circuit for adding numbers, but there is something really cool about this adder. You see, with this kind of adder, you can stack it. So just like with a 3-digit number, when you're adding 2 single-digit numbers, like 9 for example, you can add them and then carry the excess you have into the next digit. We do the same thing for our adder. You add them and then any excess you carry into the next digit. We do the same thing for our adder. This is our result and this is our carry. So if you want to add 2 single-digit numbers, we just use 1. 2-digit, we use 2. 3-digit, we use 3. 4-digit, we use 4, and so on up to infinity. And so that's how processing information works. With these logic gates you can do math, and with math you can do everything. Because once you can add, subtract, multiply, compare and all the other junks like these, all you have to do is just step 1, represent anything you want as a number. Step 2, use the CPU to manipulate it mathematically. Step 3, change back the number from a number to whatever it is you need. And we will get back to this sometime later on, but for now, the last thing about the CPU, which would be the central word. Why is the CPU central? Well, it's because it is the CPU that's like the brain of our brain, and it is the CPU which lets the parts interact. So if you'd like to manipulate an image, for example, you'd use the CPU to move it from storage to RAM. Use the CPU to manipulate it in RAM, and then move it back from RAM back to storage using the CPU. And that's why it's central processing unit, but not all the units have to be central. Some of them can be special processing units, because central is not the end of the story. We also have others like GPU for example, so the graphical processing unit. What is the difference between a CPU and a GPU? Well, let's think for a second what we need for graphics, with an example. So let's say that we have a 3D scene like this. What would 3D mean exactly in this case? Well, 3D means that if we have a cube, we can move it up or down, left or right, or forwards and backwards. But there is something interesting that happens when you move it forwards and backwards that doesn't happen side to side. The further it is from the camera, the smaller it gets. The closer, the larger. So if we have a scene with multiple cubes, then in order to render this scene, we have to go over every single cube and scale it depending on how far away from the camera it is. Now, if you were to render it with a CPU, you really have to go over each and every single one by one. But what if we had a different part, which instead of having one and powerful processing unit, would have weaker but multiple processing units? Which means that instead of quickly tackling them one by one, we could go slower, but tackle them all at once. And that's what GPUs are, and that's what they are used for, doing multiple calculations all at once. Basic idea looks like this. If you want to do a lot of something, which you can do on a CPU, like multiplication for example, then you can either do it on a general processing unit, like a CPU, or you can specialize, so basically remove all of the unnecessary bits. This makes it impossible to use your specialized unit for anything else, but it reduces the cost significantly, which means that if you really want to multiply a lot of things, it is cheaper for you to get a specialized unit. Most of the time in most computers, the only specialized processing units you'll find will be the graphics cards. But to be fair, graphic is such a general term that it is a bit vague, and if you were to create a spectrum of general to specialized, CPUs would be completely general, stuff like application-specific integrated circuits would be completely specialized, then modern day GPUs would be somewhere in the middle, maybe even more to the general side. And that's because for graphics, there is still a lot of operations you have to do, since you don't really know whenever a GPU would deal with 3D, video, or just bulk operations. So that's why they are specialized for all of them, and they use a lot of clever tricks to speed up this process as much as possible. One trick would be having an HDMI output on the graphics card instead of going back to the motherboard. The HDMI output going out obviously to the outer connections. Well, technically the screen, but this segment is about outer connections. So let's take the screen for example. If we have a cube like this, how could we possibly display it on the screen? Well, if you zoom into the screen really closely, you'll see that they are made of pixels, red, green and blue ones to be precise, which means that in order to display this cube, we just need to take the data that makes up the render, so turn this data into a red image, green image and a blue image, and then just display it. Except, how are we displaying it again? I mean, right here we do have the pixel data representing how each pixel should behave, but how will we get those pixels? How are we supposed to plug them all into our computer? We're supposed to do it individually? Well, obviously not. On a 1920 by a 1080 display, that would mean plugging over 6 million cables. So we sadly need a different way to do it, and that way is actually surprisingly simple. We just need a single cable and a standard. If you think about it, this is how our horrible way works. We basically have low amount of data turned to an image, which we turn to pixel data, which we then send on the screen. But what if, instead of transitioning to pixels here, we transition to pixels here? If we do that, we can keep a much simpler and smaller cable for a larger part of the journey. This would obviously unfortunately also mean that we need some sort of computer inside of the screen, which may not seem that great because that would increase the price of screens significantly. But if you recall the specialized processing unit chapter, you will remember that we could just make a processing unit specialized for this conversion, which would make it cheaper than processing it inside of a PC, and that's precisely what happens. Right here is inside of the PC, right here is inside of the screen, and right here is the HDMI cable. And that's how most of these outer connections work. For a keyboard, for example, we have the PC, USB cable, and the keyboard connected to keys. For a mouse, it's the same thing, except instead of keys, we have the mouse buttons and movement. With speakers, once again, we have the same thing. PC audio cable and speaker, which sends the information in the standard into the speaker movement. The key here being that we have standards, our PCs know how to send information to these standards, and then all of those devices know how to interpret these standards in order to either output or input. Practically anything. And now we should have a pretty decent understanding of every computer part. So let's go over all of them one last time. We start with our PSU powering every part. Using this power, we can get the information about some program from our storage through the CPU into RAM. Now that the program is running, it can tell the CPU to send a message into the World Wide Web and await the response. Once the response comes back its way into the CPU and RAM to temporarily save the data, now the CPU can check the data to see that it's a video, which gets sent into the graphics card, which in turn sends it through the HDMI cable connected to it to display it onto the screen. And so there we go. That's how you can see me right now. Yeah, it's pretty astonishing. Computers really are a modern wonder, and we should all really be glad that we have access to them and we live in times when they exist. Because even to watch a silly YouTube video like this one, you still need all of those computer parts. Except we're not ending the video yet, because now it's time for the ad segment. Oh boy, don't you all love ad segment? I hope you really liked the video, and I have a Patreon where if we will get at least 25 at least give a tier Patreons, then I will make It Builds a Weapon episode 2. Once again, I hate to put that behind the paywall, but I will need some budget for that video, and I'm not really getting paid with the ad revenue all that much. But also Patreons will get some additional perks. Like for example, Patreons could have seen segments of this video before the video went up. So that's pretty cool. And also right now, as we speak, there are all the segments of all the videos which patrons have access to that aren't yet on YouTube. Because I haven't finished the video, but I finished said portion and I uploaded that to Patreon. One thing though, you see, back when I recorded this originally, that was a while back, when I uploaded the preview to this video onto Patreon. And since then, couple of things happened, most notably Q&A supported on Patreon with a patron rank, thank you so much, and Useless just upgraded their Patreon from patron to contributor, which, because all of them are powers of 2, because I guess I like math or something, it means that, you know, they both kind of gave the Patreon level of support, and I just wanted to, you know, take a second to thank you both so much. I really appreciate that. It's money, obviously I appreciate it. Like, I like not starving. It's kind of a cool thing. Anyhow, more previews on Patreon. Q&A and useless. You both know what I'm talking about, but in case you'd like to support and if you want to see me build a weapon, Patreon. And once again, as always, https://MAKiTs.com/. Go to my charity and get a slice of pie for yourself. That's all still up. Every single day I stream charity checkups, which is a series of live streams I stream every single day for charity, either on this channel or the other channels, depending on, well, what I'm streaming at the moment. Also, I have a Discord server in case you'd like to chat with me. And fun fact, these doggos you saw in the storage segment, they came from the Discord server. So if you want to go check it out, I would recommend. I think that's it. Soon I'll upload even more stuff because I'm still working on the videos. And I'm really hoping you enjoy it, because for now, that'll be it. Thank you everyone so much for watching, and have a great day. Bye.